Okay, welcome back. Uh, in the last video, we did a quick introduction of the Bode plots, and we looked at a couple of examples. Some of the examples that we looked at were basically Bode plot of two constants, 100 and negative 100. 100 we saw was a dB straight line through 40 with an angle of 0. And we also looked at a second example where we did the Bode plot of h equals j omega, which basically was a straight line starting at 0, 10 to the power 0 frequency, and rising up at 20 dB per decade. Now, today we'll take a look at a slightly complicated, it's not very complicated, but we'll call it complicated anyway. So the transfer function given to us is h equals 100 over j omega. Now we could take this particular transfer function and basically work through the exact same process as we had used before here and come up with the magnitude and the phase angle of this particular transfer function. In this case, I'm going to show you a awesome property of Bode plots because of log scaling of things that allows us to do complicated transfer functions. Again, I want to emphasize that this is a relatively simple transfer function. We'll call it complex anyway. This example is going to basically serve as a model for how we want to go about solving complex transfer functions. So in this case, instead of going about and going a straight about way to solve this transfer function, we will take a look at this transfer function and basically say that this transfer function consists of two transfer functions, h1 and h2, where h1 is a transfer function which is 100, h2 is a transfer function that's j omega. Now, if you go back to what we had done in example 1 and 2, one was h equals 100 and example 2 was h equals j omega. So we are basically saying that this new transfer function for example 3, h j omega, can be written as transfer function h1, which we saw in example 1, and h2 equals j omega, which we saw in example 2. Now, how can we take advantage of the Bode plot that we've already drawn for example 1 and 2 to come up with a Bode plot for example 3? Let's consider the magnitude. The magnitude is given for this transfer function. Now, I've rewritten this as h equals h1 over h2, where h1 is 100 and h2 equals j omega. Okay, so this can be written as the magnitude is basically h equals magnitude of h1 divided by magnitude of h2. Now let's take the 20 log of h. So we basically take the 20 log of that, we basically get 20 log of h1 over h2. Now by the property of logarithm, logarithmic property says log of a over b is the same as log of a minus log of b. So in this case, log of h1 over h2 is the same as log of h1 minus the log of h2, and that's all multiplied by 20. So 20 log of magnitude of h is 20 log of this h1 over h2 magnitude, and using log property, we can say 20 of log h1 minus 20 log h2, which then gives us 20 log h1 minus 20 log h2. 20 log is the dB plot of a transfer function. Now 20 log of h1 is essentially the Bode magnitude plot of example 1. 20 log h2 is the Bode magnitude plot of example 2 we had seen. That means this Bode plot for 20 log of h is basically the difference if we have h1 plot and the Bode plot for example h2. So in other words, based on the prior examples, what we have is this is h1, that's h1, and that's h2. We're basically saying that in example 3, the Bode plot for this particular example is the difference of the plots of the magnitudes of example 1 and example 2. So take example 1 and subtract example 2 from it, and we'll end up with the magnitude for example 3. Now let's take a look at the phase before we start drawing things. So the phase plot, h equals h1 over h2. So both of these transfer functions are basically phasors or complex numbers. So in the division of two complex number, the angle of h, so the angle of h, if this is a complex number and that's a complex number, h is basically the angle of h is simply the difference of the angle of h1 and the angle of h2, right? So the angle of h1 subtract angle of h2 gives me the overall angle of h. So angle of h is angle of h1 minus angle of h2. Now angle of h1 is the Bode plot, phase plot of example 1. And angle h2 is the Bode plot of example 2. So that means the Bode plot for this, the phase angle plot for this is essentially take the plot of h1, phase plot, take the phase plot of h2 and subtract those two out to get us uh, the new Bode plot. Okay, so let's draw those out. So I've drawn that right here. So the red line that you see is the magnitude plot 40 dB for example 1. 0 degrees angle was the example 1. The black line was the 20 dB per decade rise for example 2. So the red line minus the black line gives us the transfer function Bode plot magnitude for example 3. So here we have the red line is at 40, the black line is at 0, so 40 minus 0 gives us 40. A decade later, let's say, a decade later at this point right here, so we're looking at where my cursor is right now, the red line is still at the red line is still at 40, the black line is at 20, so 40 minus 20 gives me 20. This point, uh, that point right there, the red line is at 40, the black line is at 40, so 40 minus 40 gives me 0. So the resulting blue line that you see is at 0 dB. So I'm starting to trace my angle down at a rate of negative 20 dB per decade slope for this based on the red line minus the black line that leads me to the blue line. Similarly, for the phase angle, the red line, we said that the phase earlier, we said that the Bode plot of the phase of h is the difference of the plots of phases of example 1 and example 2. So example 1 was the red line through 0 degrees. Example 2 was 90 degrees right here. So 0 minus 90, since it's the same across all frequencies, so 0 minus 90 is negative 90. So the blue line is the negative 90 plot for 100 over j omega. Right? So this example was basically an illustration of how to do Bode plots for somewhat complex uh, transfer function. Bode plots can basically be broken down into smaller Bode plots, and we can add the magnitude and the phase plot of the smaller ones to build a Bode plot for a larger transfer function. So this was an example in that. And then in the next video, you'll see an example of a slightly more complicated problem where we'll again break a larger complex transfer function into smaller plots and work from there.